Okay.
Good evening to one. It's my pleasure to welcome you all to the fourth keynote lecture of SECON 21. Now, before we begin, I request all of you to please switch on your videos and mute your audios till the end of the session. Also, if you have any queries regarding the topic, please don't hesitate to put it up in the chat box. I now welcome Gogul Ajit to address the gathering and introduce our keynote speaker.
Thank you, Sanika. A warm welcome to everyone present here. With great honor, I'd like to welcome the guest of the day, Dr. Arjun Jayaprakash, who will be the speaker for today's fourth keynote lecture based on challenges in earthquake catastrophe modeling. I also welcome the audience who have graced the event with their presence. With great pleasure, I'd like to give a brief introduction on our chair, Dr. Arjun Jayaprakash. A senior earthquake engineer at Karen Clark and Company, KCC, based in Boston, Massachusetts. Sir is an alumnus of the National Institute of Technology, Calicut, and North Carolina State University, Raleigh, and have worked on research in the areas of seismic design structures, ground motion characteristics, and earthquake risk assessment from the purview of performance-based earthquake engineering. Currently, Sir works in the catastrophe modeling industry and focuses on losses caused by catastrophic events and natural hazards, especially earthquakes. Sir is part of the team at KCC that develop and improve seismic loss models for different regions and clients around the world. Hearty welcome to you, sir. With all our respect, let me invite you to take over. Once again, welcome.
Thank you. So should I start sharing my screen? What do you guys see?
We're seeing a white screen, sir.
White.
Okay, I think I'm not seeing that screen. Let me figure something out.
It is good now.
Okay. All right. Thank you for that introduction. So just to reiterate, my name is Arjun Jayaprakash, and I am a senior earthquake engineer at a catastrophe modeling company. We're located based out of Boston, Massachusetts. Before I begin, I wanted to express my thanks to the conveners of this conference for inviting me. It's really a privilege to actually deliver a keynote in a conference, especially with when you look at the other keynote speakers who are like stalwarts in the field. So as I was introduced, I'm into earthquake risk modeling business. So basically that involves putting together like a multidisciplinary team to actually come up with what we call as earthquake loss models. Now you'll see what a loss model is soon enough, but the team actually consists of like structural engineers, ground motion specialists, soil mechanics experts, as well as seismologists. And even there are concepts from earthquake economics that would have to be used when we're creating these earthquake loss models. So without further ado, let me hop on to the presentation. So what I want to do today is to achieve a few things. So first is give you all an introduction of what catastrophe modeling actually is. It's somewhat an unfamiliar field. So for those of you who are not familiar with it, I'll give this would be an introduction to that particular field of inquiry. Second, I also want to point out pitfalls along the way, or like things that we're missing in the current implementation of these earthquake risk assessment models. And it's very important to know as a user of the assumptions that go into these models. And some of these assumptions are, in my opinion, very simplistic. It's not because of lack of actually trying to bring nuance, but it's just because that there isn't enough research in certain areas that would be useful in catastrophe modeling. Okay, so let's hop in, and I like to start with this particular slide, which is a quote that I find very useful to convey what where I'm standing from. So E.P. Box was a former statistician who, in 1976, said that all models are wrong, but some are useful. Now, in this case, he was particularly within the context of statistics, but I think that this is more widely applicable, especially in the field of engineering, where engineers are they mostly deal with problems, and they're very goal oriented, and the goal is to solve a particular problem. It doesn't matter if the solution works or not for any other kind of problem. So that is something that has to be kept in mind throughout this presentation, and I'm sure throughout your life, because any model has to be contextualized in a specific area or problem. So talking about goal orientation, within the earthquake risk mitigation community, let me make sure that, okay, so can someone confirm that you're only seeing the white screen and nothing else?
Yes.
Yes, we are only seeing the presentation.
Okay, because I get pop-ups when people are joining the meeting, so just making sure that you're seeing everything. Okay, so talking about goal orientation, within earthquake risk mitigation, there are, at least at the moment, two prevalent schools of thought of how or what problems are to be solved in the case of earthquake risk. So first are the performance-based models. So basically, these are models that are much more rigorous and technical. A lot of studies go into these models, and most of academia, basically researchers, publish articles that directly contribute to these particular performance-based models. Now, what I mean by that is one outcome of a performance-based model is whether a building of interest attains 50% damage in the next 50 years. So basically, most of what performance-based models try to address is the risk to any specific structure. It can be a high-rise building, it can be a dam, it can be a bridge or any power plant, or any specific structure of interest is what these types of models address. There's another school of thought which is much simplistic in their buildup, So basically, these are built by more simplistic models, and a lot of economics and statistics come into play here, which are known as catastrophe models. Now, what catastrophe models are most interested in are not just a single structure, but an entire portfolio of structures. So, for example, if you think of governments, they own multiple structures within a specific geographical region. Or if you think of some of the insurance companies, they actually sell insurance, homeowners insurance in natural hazard prone areas. And that means that they have to be aware of the risks that might affect their particular portfolio of insurance structures or insured structures. And one outcome of a catastrophe model is whether is to give whether or to give what amount of money that you might expect to lose in the next, say, 5, 10, or 50 years. And you can immediately see the difference in the target client. On the left side, for performance-based models, a user has to be an expert. So he has to be a specialist in whatever is being modeled, because he has to be aware of he has to be able to use that model. And he has to he or she has to be able to speak or understand the terminology of probabilities. For example, if you say something like 50% damage in the next 50 years, you have to know what that actually means to be able to use that model. For catastrophe modeling, however, these are more CEOs of companies that may not have the specific expertise in the area of natural hazard or engineering, but it's more contractable, or basically more comprehensible to them, when we talk about the monetary aspects of risk. So I want to make that two different types of models, or the differentiation, clear. So let's dive in deeper to an example of how performance-based models and catastrophe models interact or actually contribute to the global cause of earthquake risk mitigation. So if you take the example of New Zealand, it's a very seismically active country, and it's probably one of the foremost in research as well regarding earthquakes. One of the outcomes of performance-based model are these seismic hazard maps. What these hazard maps give us are basically the level of hazard, probabilistic hazard, that one might expect in any location within a given region. So for example, on the left side, what you see is a map of the 2-second spectral acceleration that can occur with a probability of 10% in 50 years. That's like a 500-year return period. And on the right, it's like a 1,000-year return period. So if you notice, if you were to look at closely to any particular region, for example, Christchurch, which we'll talk about in a few slides, Christchurch lies within like a low to moderate level of seismic hazard. And that's given as an outcome of performance-based models. And the users are mostly code builders or structural engineers who have to account for this level of hazard when they're designing a new building in a specific region. Whereas an outcome of a catastrophe model is what we call an exceedance probability curve, or EP curve in short. What that means is that remember, we're talking about losses. So any dialogue that has to be had within the context of catastrophe models are always in terms of losses. So we're informing a client, for example, in this case, if it were like a government of a region in New Zealand, we're informing them that a loss of about, let's take an example, starting from the very left bar, a loss of about $130 billion has a probability of occurring of 0.002 in the next year. So any exceedance probability curve addresses the next year. And it is built that way because a client, like an insurance company or a government, always plans immediately to allocate funds for the following year. Let's take another example. There is a much more probability of 0.1 or like a 10% probability of a particular entity losing about more than $1 billion within New Zealand. So that's what the lower or the just first from last number is saying. And the last number is also important. It's in short called the AAL. It stands for annualized average losses. What that gives is the mean of the EP curve. So for example, it basically tells you that on average, New Zealand can expect to lose about $1 to $2 billion every year because of earthquakes. These can also be shown in terms of a map because the government might also be interested in allocating different shares of their budgets to different regions based on the risk that in that region. Now, what you might, if you had observed keenly in the previous slide, you might see that the regions of high hazard does not coincide with regions of high risk. Now, that's because risk is not just the seismicity part, but also the amount of value that is exposed. So a much more population dense area, even though it has a smaller earthquake, will incur a lot larger risk. So what I've gone through in the past couple of slides are models that are continuously updated. And these exist in real time. So basically, the code gives you the outcome of a performance-based model, and you have to, as a structural engineer, you have to follow that. Whereas in terms of a catastrophe model, the client is aware of how much of a loss on a probability basis can be expected. But what happens when an actual earthquake strikes? And this happened on February 22nd in 2011. So this is actually a pretty recent earthquake in Christchurch, in New Zealand. And this also occurred only about 4 or 5 months after the Canterbury sequence of earthquakes, which also slightly affected Christchurch, but not to this amount. But the previous earthquake had made some of the structures much more vulnerable in Christchurch. And the reason I picked this particular event is because this is an interesting case study as to how much of a damage can be incurred with an event of a medium magnitude of 6.2 in a developed nation, and that probably has the best seismic code in the world. So even though the magnitude was a 6.2, Christchurch was devastated. So basically, there were all kinds of damage that were seen. There were reinforced concrete buildings that failed. There were steel structures that deformed to an extent that they totally had to be demolished. And there were houses made of masonry and wood that were also completely destroyed. And a total of 185 people lost their lives in this particular event. Now, considering other major natural hazards like earthquakes and tsunamis, 185 people is, while each human life is important, statistically speaking, it's a much lower number. And that is because of the much better code design in New Zealand. Although they still had to, they still estimated about a $15 to $20 billion economic loss because of this event. Now, economic loss includes everything. It includes direct and indirect losses to the economy, and a property loss between about 5 and 7 billion US dollars. Just for context, $1 billion US dollar amounts to like 7,000 for Indian rupees. But what's interesting and what's the point I want to convey is that New Zealand were aware that this would happen, and the insurance companies as well as the government were aware that were aware of the funds that would have to be paid out once this had happened. So New Zealand has an interesting structure for insurance. The government itself owns an agency called EQC that insures homeowners against seismic risk. And it turned out that they actually had funds left after all of the payouts. So this is an example of a system actually working. Whereas if you take, on a sharp contrast, if you take Haiti, an earthquake struck the island of Haiti on January 12th in 2010. And this was a much larger earthquake, it was a magnitude 7.0. But I'll give you all a few moments to think about how many people lost their lives in this event. Now, some of you might have guessed it, but the total number is still uncertain, but official estimates range between 2 to 3 lakh fatalities. So that's the definition of a bad catastrophe. In addition to loss of life, Haiti, the government also expected a loss of, or estimated a loss of $10 billion as a consequence of this event. Now, as opposed to New Zealand, Haiti is one of the poorest countries in the Western Hemisphere. So a $10 billion loss is no little deal. And another important problem that they faced was that most of the structures or assets in Haiti were not insured. So only about 500 million out of that 10 billion was paid out as insurance. And the rest had to be taken care either by the government's funds, which lacked enough funds, so Haiti had to depend on a lot of international aid. And international aid mostly comes from multiple countries, as well as disaster relief agencies like the United Nations Disaster Relief Fund and the World Bank. So it's not just wealthy countries that are interested in catastrophe models, but also global entities like the World Bank and the United Nations that have been clients to most of the CAT modelers. And when I say CAT modelers, it is just a short for a catastrophe modeler. So I might use that term, but it's just easier to say. So one of the public sector giants or the public domain experts in catastrophe risk modeling is a organization based out of Italy called the Global Earthquake Model, or the GEM, and they estimate around $45 billion of annual earthquake loss globally. So that means that GEM claims that every year the whole planet can expect to lose about 45 billion US dollars just to earthquakes. Now, that's all good. How does GEM make such an estimate? So it seems like an impossible undertaking to actually give an estimate of the total loss that the whole world can incur because of earthquakes. So the rest of my presentation actually focuses on how that is done. I chose to use the wider aspects rather than going deep into each of the technical nuances, so that you get the biggest picture of what a catastrophe model is. So let's take a few steps back and let's turn our textbooks to how, if this problem were posed to us as students, how would we have approached this problem? So let me state what the problem is. So think about a geographical region. So this is just a map that I created. It looks like a rubber duck, so let's call it Duckland. Let's say in Duckland, you have a building that you're interested in. All right, so you have a building that you either own or you are a stakeholder in that building. And you know that there are seismic sources near your building or near the location that the building is. And mostly these seismic sources are either faults or tectonic plate boundaries. and we'll talk about tectonics a little bit later. So let's say that an event actually happens in the source. So what you see here is like a generic cartoon of an earthquake. The red shows high gram motions and the green shows low gram motions. So this is basically a field of gram motion values. We also call it as a footprint of the earthquake. So you can see that your particular building falls within this earthquake. So let's say we know how to calculate this field, and we'll talk about gram motion prediction equations and how they're useful in actually estimating these. Let's say we know the ground motion that your structure undergoes, or basically the response spectra right on the location of your structure. And that's given by the ground motion model. So if we know the period of your structure, it's common knowledge, at least for our structural engineering friends here, that if you go to the period and response spectra, you can calculate what the acceleration, what the peak acceleration is to your structure. Once you have the peak acceleration that your structure undergoes, you can use something like a fragility curve to get the probability of different damage states that your building could be under. So for example, if you know that the acceleration is somewhere here, you just go up the curve and read the probabilities between 0 and 1 of each damage state to be, of each damage state that the building might have been under. And clearly, so these damage states are also very subjective. Any particular researcher working on any particular building would define a damage state based on his expertise, and that may not be conveyed to the whole community. But generally speaking, limit states are classified as serviceability, damage control, or ultimate. So once we have that, we basically get to what, again, I'm repeating here, we're basically getting the probability of damage that your building is under. But we still do not have a loss value. So my effort in the following slides would be to kind of bridge this gap between damage and loss. So before doing that, let's take a look a little bit deeper into what fragility curves actually tell us. So basically, again, fragility curves are curves, mostly log normal cumulative distribution functions that give us the probability of any building or any structure incurring a specific damage state, given a specific acceleration. And most of these are developed for individual components or a specific construction type. For example, there are many, a myriad of research that focuses on how to develop or that focus on what fragility curves are for different types of buildings. For example, on the left, you see a two-story timber house put on a shake table, and you can develop fragility curves based on that. Or you can have a quasi-static loaded tests like what you see on the right on reinforced concrete or masonry shear walls. Apply lateral loading and come up with the different damage states for them as well. So if eventually what the researchers end up doing is develop a numerical model that is calibrated using experimental research, and then subject that numerical model to multiple simulated ground motions. It could be actual recordings or simulation of ground motions. The reason we have to do this is because shake tables are not available everywhere. It's not an easy thing to do. It's not an easy test to do. So that's why we depend on numerical models. Now keep that in mind, and remember that all of these numerical models are very contextual. Each model represents a specific construction type or a specific material type. And another thing that we have to keep in mind are that the fragility curves that come out of these these numerical models, the x-axis is the acceleration sustained by the structure, and that structure has its own period, right? So even though we have a whole database of fragility curves, the question still remains as to what fragility curve we have to use, because our building can be of a different period than the fragility curves that exist. But for CAD modeling, we don't have to be bogged down by this particular detail, and we can leverage the law of large numbers. So for all of you statistics buffs out here, here's just a summary of what a law of large numbers mean. So it just means that the observed mean approaches the theoretical mean if you have a large enough number of trials. For example, if you were to roll a die, a six-sided die that has numbers 1 to 6, if you have enough, if you give enough trials and then calculate the average of all of them, it will equate to 3.5, which is the numerical average or theoretical average. And how do we make use of that in CAD modeling? So here's how. So let's go back to the duckland example that we had. Let's say we have the ground motion occurring somewhere near, and then there are different locations that we're interested in. Now, each of these star is actually a combination of many buildings. So this could be an entire city or a zip code. And the reason why we use this is because it's really an intractable process of developing the full inventory of a country at a country level, and go to each building and decide on the properties of all those buildings. So, for example, this city might be consisting of all types of wooden structures, masonry, concrete buildings, or even steel buildings. And again, because we are using a mixture of hundreds or even thousands of structures of multiple properties, it is sufficient to have a single mean curve that can give us losses for the entire city rather than for each building. And that is the specific context of CAD modeling. So let's do an actual example problem here. So let's assume that the total value of one of the star is about 100 million. And that's, it can be any units. It doesn't have to be in US dollars. But let's say it's 100 million. And that's basically the sum of all of the exposed value of buildings in the city. And remember, the fragility curves would give us as to what percentage that, or what percent, or what's the probability that your structure might be under. So if you translate that into a city level, it would actually give us what percentage of buildings would be under that specific damage level. So for example, in this case, let's say a standard fragility curve tells you that for this particular city, the number of percent or the percentage of buildings that are in a slight damage state is 40%, and the ultimate damage state is like 2%. Once you have those numbers, a bridge between damage and loss is what is known as loss functions. Now, loss functions, although it sounds fancy, it is just a number that you multiply the damage with to see what you get for a loss. So let me explain what one example is. So for a loss function of 5% means that if your building is in the slight damage state, your loss would be 5% of the total value of that building. So if 40% of buildings are in slight damage state, then 40% multiplied by 5% would give you the total loss of $2 million just because of slight damage. Remember that the total loss of the city is 100 million. So it's like 100 times 0.4 times 0.05. That will give you 2. And similarly, you can do the same thing for other limit states and calculate the loss. And then if you add up all the losses, that would give you the loss for the entire city. So one star would cost you about $15 million because of this earthquake. And if you can do this for one star, you can do this for all of these stars. And that is eventually the total loss that would be incurred by due to as a consequence of this particular earthquake. Now, I haven't talked about how these loss functions are calculated in the CAT modeling industry, but this is just a bridge between performance-based outcomes and the final loss value that we need. And these stars that I've just thrown around in this map are generally known as exposure. So whenever we talk about the term exposure, it is the location and just a associated monetary value to that location. And that monetary value can come from hundreds or thousands of structures. Now, the question that some of you might have right now is, what is the basis of these loss functions? And I don't have an answer for you. These were created, these were based on expert judgment and are pretty much arbitrary. And there is a real lack of research actually at least proving or disproving these numbers. So that might be something that future researchers can take up and try to come up with these loss functions. Now, let's look at a real-world example of what an exposure is. So let's take a look at India. Exposure points, so these stars that I've shown in the earlier slide, can be scattered around the whole of India like this. If you take a closer look at, like, say, Kerala, what you would see is that the density of these points goes down. So even though it seemed that the whole of India is covered, it is not that way. If you zoom in even closer into, say, Kochi here, what you would see is that a whole city or a zip code is represented by just a single point. And that's basically, this is probably the best resolution that a CAT modeler or even a performance model based total risk assessment model would have for exposures. So it doesn't matter if you know what your particular masonry structure or how your masonry structure performs in an earthquake. It's all about agglomerating the entire vulnerability function as a single mean curve for each of those regions. And these can be region specific. And the region specificity has to do with how much of a percentage of inventory of each building type is concentrated in a particular location. So CAT modelers use vulnerability functions. So to go from ground motion intensity, remember we have a ground motion field that can be generated by ground motion prediction equations. If you know the intensity at the location of interest, you can just go up this curve and plot out the value on the y-axis, which is known as the MDR, or mean damage ratio. What that means is, let's say if the MDR is 0.5 at the location of interest, you would just multiply 0.5 with the total value that was exposed in that on that location. So it's really simplistic, but because of the law of large numbers, it actually gives useful results. Now, how do we come up with these vulnerability functions is the next question. So what we do is actually combine, this is just repeating of what I just said. So what we do is actually combine all of the vulnerability functions that we have, we can get published articles for. So for example, there might be articles talking about how unreinforced masonry single family housing, which is a largely prevalent structure in Kerala, perform under an earthquake. Or there could be articles about how reinforced concrete school buildings perform. So it's basically a lot of literature review and coming up with these individual curves. There could also be ductile frame commercial buildings. So these are just examples of what can be out there. And depending on how much percentage of these are there in their particular location or a region, which is known as the inventory, we weight average these curves to combine them to find a final vulnerability curve for our region. And the vulnerability curve for Kerala might be different from Tamil Nadu, or it can be different from Punjab. So that's the idea here. Now, one important thing about vulnerability curve is that there is a problem that we have observed, at least in the past few years, when we use numerical versus empirical. when we use a numerical vulnerability curve, which is basically an agglomeration of multiple fragility curves using loss functions, it generally tends to be a CDF or cumulative distribution function of a log normal distribution. But in reality, if you were to observe actual loss data from actual events, what you would see is a shape like this. At lower gram motions, it doesn't start to damage. So structures just don't damage it. There can be many reasons for this. The inherent uncertainty associated with earthquake can be one. Also, a small crack may not be reported as well. People are quite sufficient to live in a house after an earthquake that just has a small crack. But a cumulative distribution function predicts a non-zero loss the moment it has a non-zero acceleration. Also, at the higher zone, at more than 1.2 g of 0.3 second acceleration, what has been observed is that a 60% or a 70% loss to a building would eventually deem it as a total loss, and insurance people would eventually. It's better for them to just pay the entire amount rather than repairing the specific aspects of what was damaged at these high levels. So there's a steeper curve in actual that has been seen in actual events. And when I see that has been seen in actual events, what I mean are based on reconnaissance damage surveys that have been done by both public and private entities after major earthquakes. So, for example, let's take the event that we just discussed about the Christchurch event. The damage surveys, the way they work is that we make a sweep from the lower ground motion to a higher ground motion. Once we have the ground motion field, we know where to look. So basically, if we were to look at a location at a lower level of ground motion, you might only see non-structural damage. And you can start to see as you make a sweep, you can start to see what level of damage or what ground motion initiates a certain level of damage and what ground motion ends a certain level of damage. If you go further in, you can start seeing structural damages like failed columns, etc. So these kind of give us an idea of what damage level can be observed or loss level can be observed at specific ground motion levels. So how do you validate these loss curves and the exposure? So exposure is also something that we have to develop independently. Each model has their own team that develop these. So how do we validate that? So let's take an example of South America here. South America is pretty famous or infamous for being, or for the west coast of South America being right around the Ring of Fire, which is basically a ring where most of the large earthquakes have occurred in the past. And South America, or the west coast of South America, is actually a source for some of the largest events ever recorded in human history. So, for example, there's a 1960 Valdivia, Chile earthquake, which had a magnitude of 9.5. And there is a 2010 Chile earthquake that had a magnitude of 8.8 in Mali. These are just a couple of examples. And what you see here are, again, as I've said, these ground motion fields are generated by ground motion prediction equations. We'll talk about ground motion prediction equations in a couple of slides, but bear with me for now. So once you have these for significant earthquakes in the past, what we can do is actually model them using these ground motion models and then get a loss based on what our exposure and vulnerability is for that region. So the task is to compile as big of a database as possible of past significant events. And it has to be in the recent history as well. Simultaneously, what we do is we look up, we make a rigorous search of the internet based on news reports or published articles or even databases that provide actual losses for these types of events. And then mostly these losses can be in terms of a range. So there will be a higher bound and a lower bound for actually observed losses for these events. And then we would be able to, after modeling these events and comparing these with the modeled prediction, we can build plots like these. So we superposed our prediction with the actual losses that were observed from those significant events. Now, these would be trended to how they would be in 2021 monetary value. So even though the events have occurred in the past, we use economic principles to kind of trend the value to the latest dollar value. And the task here, after we get this plot, is basically to minimize the deviation from actual and observed, or actual and estimated. Okay, so if we finally get, so we've talked about how we can use modeled historical events to validate exposure and vulnerability that we develop. Now, but how do we model these events? So finally, we get into the ground motion prediction equations. These are equations that simply give you the acceleration at a location given a certain amount of input. So if you know the epicenter, the location of the epicenter, the distance to the site, the magnitude, the GMPs would give you the spectral acceleration at your site. And it would give us the acceleration for the whole period range. For here's an example. This is the Boer and Atkinson GMPE for active shallow crustal events. And what you see on the x-axis is the range of periods. On the y-axis is the acceleration. And you see different curves for different magnitude levels. And this particular plot was developed for a site of 0 kilometers from the source. So that's like right at the source. So now the question, the problem, here's another problem that we observed in our practice. When we're trying to model using GMPEs, hold on. When we're trying to model using GMPEs, what period do we use? So for example, if we, the GMPEs provide us with a range of values, and the values that are of interest to us, because we're using the law of large numbers and because we're using a portfolio, it is generally accepted that a prototype low-rise building corresponds to a period of 0.3 seconds. A mid-rise building corresponds to 0.5 seconds, and a high-rise building corresponds to 1 second period. And so in CAD modeling, what we end up doing is make 4 different footprints, or 4 different ground motion fields for each of these different periods, rather than doing it for the entire spectrum. So there's PGA. So here's an example from the Bhuj earthquake in Gujarat. Here's the PGA ground motion footprint. So this is developed using a ground motion model that is applicable for stable continental regions like that in Gujarat. Here's the 0.3 second footprint, here's the 0.5 second, and here's the 1 second. So as you can see, the 0.3 second footprint geographically looks much larger than everything else. That just means that low-rise buildings are in much more of a risk due to this event than high-rise buildings, especially far away from the actual source. However, the high-rise buildings at the source are still subjected to a lot of damage because of this earthquake. And that's evident by the red portion in the 1 second footprint. So, for example, there have been reports of buildings or houses in Karachi being damaged after the Bhuj earthquake, but there were no high-rise buildings that were damaged in that location. Most of them have been isolated in Jamnagar and Bhuj. So now next is a question, it's all said and done and we have the best GMPs that we can use, but does the GMP really give us what we need? Here's one case study that kind of questions that assumption. For example, GMPs are generally, even though they are an equation, it's a regression equation, and there's a lot of uncertainty around the data that was used to regress or make that regression curve. So if you were to look at the 1999 Chi earthquake in Taiwan, which was a magnitude 7.7, this earthquake is important because this is probably one of the most well-recorded earthquakes. So recorded in the sense that there are actual acceleration records from multiple locations. So if we were to plot the peak acceleration records from actual locations as a function of the rupture distance, you would see these triangles. And what the GMPE for this particular region says is what is shown by the red line. And you can clearly see that if you were to just simply use like a moving average fit to the actual data, the lower distances, it kind of, GMPE kind of overestimates the acceleration, which means that you have to be aware whenever you're going to a specific region and using a GMPE, you have to be aware of the fact that the specific GMP that you're using may or may not work, and you have to test it out. And if you find that it doesn't work, either you have to adjust your own adjust the GMP to the specific region, or just have in mind that the losses that you would be predicting would just be higher, and that is acceptable as well. Okay, so far we've gone from exposure to vulnerability functions to how we model a single event, and we use that to get losses from a single event. But again, remember, we started this by posing the question as to how a probabilistic view of future events would look like. So as you all know, a past earthquake event will not occur again. The future earthquake event would be completely different. So here's an example of how we go from probabilistic to or single events to a more probabilistic set of events. To go to a probabilistic set of events, what we need are seismogenic source models. For example, there are almost the entirety of the planet have been studied by seismologists and have been categorized as different types. So the plate tectonics can be either active crustal, which means that there is a chance that there's much more frequency of faults rupturing within that region, or it could be stable continental, where there are faults and they can generate ground motions or earthquakes, but they're not as frequent. There are also subduction interfaces that are basically plate boundaries, which cause huge earthquakes and are major causes of tsunamis. So this is just my representation of a cartoon of how it looks for India. If there are seismologists listening to it, please don't take me to task, because I accept that this is not an accurate description. This is just to prove a point that there are regions like these around any region, and these regions can be then subclassified into further pieces. So, for example, in the green region, you might see a few more pieces that were carved out of the whole piece. Now, for each piece, the seismologists, what they do is develop what they call as the magnitude frequency distribution. What that is basically on the x-axis you have magnitude, and on the y-axis you have frequency. In this case, I've also renamed frequency in terms of return period. Return period is just the inverse of frequency. So, for example, a frequency of 0.0001 would just mean a 10,000 year return period. So what this tells us is that the green line is the frequency distribution for, say, an example piece of the tectonic region that we're interested in. And this tells us that a magnitude of 6.5 has a frequency of recurrence of about 100 years. So every 100 years in this particular piece of land, there's a chance that a magnitude 6.5 or greater can occur. So we can have these, we already have these for all of the different pieces that make up the whole tectonics of any region that we want to address. And then once we have the rates, we can use the Poisson process to sample these rates. So basically, for each magnitude that you're interested in, you can decide on what level of rates that you would need. And this can be any process that you like. So different modelers try to approach this differently. So there are techniques like random sampling, where you either use latent hypercube sampling or something like that to generate from within a given set of magnitudes events that correspond to the rates given by the magnitude, MFD. Whereas there could be stratified sampling, where you actually choose sets of events or sets of magnitudes, and then you already acknowledge that you're going to use those magnitudes, and then you just sample the rates from the magnitude events or from the MFD. There are also another method that we use in my company, KCC. We use the process called characteristic events or characteristic magnitudes. We sample actually from the y-axis. So remember the EP curve? The clients are actually interested in losses for different return periods. So we just look at the different return periods on the y-axis and then sample the corresponding magnitude that we need to model to give the return period in question. So for example, in this particular plot on the right, we can decide that we want to model a 5.85, a 6.6, and so on. So once we decide we model those, the next step is to basically cover the entire land of the area that you're interested in. So again, going back to Duckland, remember we had a single footprint like these, we talked about it. What we want to do is we want to assign possibility that any star in this, any exposure point in this map can be affected by a seismic event. So we basically cover the entire region with many different magnitude footprints. And this might seem odd, but what we do is that the probability of each of these events occurring is based on the MFD. So even though there might be an event at a very low seismic region, it just means that we are just acknowledging the possibility that there could be an event, but the probability is very small. And once we cover the entire region, we basically create thousands of earthquake scenarios, and each of them would have their own recurrence rates associated with them. And we can use these recurrence rates to actually use a stochastic sampling to create or simulate a catalog of, say, 100,000 years. So what I mean by that is a Poisson sampling would just mean that depending on the rate of each of these events to occur, you create a scenario where you sample for 100,000 years. So for example, you take the first year and then you look at the rates and then you you just use Poisson sampling to see if the rates can give any event in that particular year. If it gives, then you record that year, you go to the next. Some years can not have an event at all, but it's just basically simulating a 1,000-year, 100,000-year future of earthquakes. And then if you order that event, the results of that simulation, what we get is the exceedance probability curve that we looked at in the first few slides. And the AAL, again, is what's the important number here. The AAL is the $45 billion that you saw in one of the slides that GEM claimed to be the annual average loss expected for the entire world. And AAL is, in fact, part of the EP curve. So basically, that gives basically a wide picture of what all goes into these models and some of the interesting assumptions that go into these, which you may or may not agree with. And I'd like to hear comments or questions regarding these as to if you have objections to this. So to summarize, I started by motivating, showing you how a specific event can have huge impacts, even if it happens in a wealthy nation like New Zealand. And I pointed out how a large loss it can be incurred by different countries of New Zealand and Haiti. and I showed the two different scenarios, how they could have completely different responses to that event or that loss. And then I pointed out how GEM claims that we would lose about $45 billion every year to earthquakes, or expected to lose. We talked about exposures, how exposures are agglomerations of hundreds of structures and are used to basically cover the entire world if we want to figure out a way to model the earthquake risk for the entire world. Then I moved on to how we use vulnerability functions, which is nothing but a curve that gives us the number or factor that we have to multiply the value associated with an exposure with, given the level of ground motion for each event. And then we talked about how each event is created, and these are usually used by using ground motion prediction equations. And we talked about how the different periods of ground motion prediction equations was not necessary. We only use 4 different periods, and these are the ones that are most important to us because of how low-rise, mid-rise, and high-rise structures can be considered as a general class. And then finally, from a single event to go to a probabilistic set of events, we talked about how we use seismogenic models to give us the rates of each magnitude of events occurring around the world. And then we just use the ground motion models to model all of those, and then use sampling techniques to generate multiple events or thousands of events with the appropriate rate of recurrence. And the losses calculated out of these events would eventually give us the final peaker. So with that, I come to the end of my presentations. I hope I didn't go, oh, maybe I went a little bit off time here, but I hope if you have some time for questions as well.
Thank you, sir. Now, if anyone has any doubts or clarifications regarding the topic, please raise your hand or put it up in the chat box. Also, participants, please note that the link of the feedback form will be soon available in the chat box, and make sure that you fill it so that you can receive your certificates.
Can I ask a question, Arjun?
Sure.
Yeah. I was actually working on something like a liquefaction problem in the Kerala region. So one of the questions that was raised at that point was, what is the relevance of such a study? Because given the probability that the occurrence of a large event in a zone, I hope you know the Kerala is in the the least, zone 3 as per the Indian status. So I was wondering, how do we make use of the technique which you explained to justify study for a large event in a location where the probability of a large event is low. So how can we? I hope you are getting the point. Right?
Yes, yeah, that's true actually, and that's something that I guess researchers as well as modelers have a tough point conveying, especially for towards like a funding agency. Most earthquakes, the timeline of earthquakes are actually much larger than human perception. So we kind of ignore the impacts of a large event. It doesn't. Let me see how we can justify that. There is always a possibility, because Gujarat is a good example. Even though it is in a stable continental region, I mean, now it is being debated whether the source is stable continental. But I think some of my colleagues, I've asked this around before I present this, as some of my colleagues thought that it is actually a stable continental region. The occurrence interval would be in hundreds of years, right? So we may not see another Gujarat in our lifetime. But it still had a major impact on the state as well as the country. I would say, and especially liquefaction is something that is much more relevant to a larger event rather than a smaller event.
Yes.
Because you need a high duration as well, and a large shaking. So I would just say I don't know exactly about the probabilistic models that have been published in India, of India, or the Kerala region, but I think there might be something that is available there to showcase that it's even though the recurrence interval is huge, it does not preclude from anything happening there. And if anything happens, the vulnerability of, especially vulnerability of regions that do not expect a large event is much higher because they're not prepared for it, and the code following would be much lax. They may not follow stringent code criteria as well. So given all those working against you in case of a large event, that these types of studies would become a much important. I guess it just means that even though the recurrence interval is large, we cannot ignore the fact that there could be a large event, basically. And I don't have evidence on hand for the Kerala region because I haven't studied that. But I am sure you might be able to find resources like that. Or I think I just saw, whenever I was doing some research for this presentation, there is a probabilistic seismic hazard assessment that was just done by GEM for the whole of India. They might have some data. I don't know if they made it public, but they will eventually make those public. They might have those data for state specific for India as well. Sorry if it doesn't answer your question, but that was just my take on it.
It does give me some direction. So can I see that as an opportunity in terms of looking at the vulnerability of the region and then come out with models for this particular location?
Especially in US, what we have are liquefaction maps where they have these liquefaction susceptibility maps. So it's not the entire nation that is covered by it, but there are regions or patches of these that actually amplify the ground motions that are developed by using the ground motion models. So that's how a CAT modeler addresses this. There are maps or patches within regions that basically go into the model, and if your structure is within that, you can expect a much higher loss. So one contribution to at least my field would be developing these patches of areas on like a latitude and longitude polygons of these liquefaction susceptible areas within India. If we have that, then it's a great data for clients as well to actually decide whether to invest in that location or not. So any liquefaction susceptibility is also, the data is very rare. When we try to find it, it's only there for important seismic regions around the world, but not otherwise, even though they have these risk of having large events. So yeah.
Because I just wanted to mention another thing, because there was a recent flood couple of years back in Kerala that in fact prompted a lot of people, because it was a large event with a probability of around 100 years. So people started mapping and looking into those studies again. So earlier, we were not doing such studies for quite some time, and a large event triggered people to look into creating maps, which will, hazard maps, and creating studies based on that. So
yeah, that's always the case. I mean, only a large event can like push people to do something about it. Although, and that's also because most people do not completely comprehend the concepts of probability. I mean, the stakeholders, what I'm saying, not like specialists. But that's one thing that stakeholders need to basically push them to actually provide funding for something like that.
Just one more thing. Most of the participants are actually undergraduate students. So would you like to suggest some basic textbooks they could refer to, or some references from there they can learn the basics of vulnerability and probability mapping and related to civil engineering?
Textbooks, this is a kind of a recent field, and there aren't many textbooks for CAT modeling as such. But for risk assessment, I think rather than textbooks, if they were to follow articles or people that do research in these areas, that would be a better part. And I can suggest some universities that do good research. So basically, if you were to like, Google Scholar is a really good what do you say, platform to actually look for information online, especially articles that are peer reviewed. So there are work done in Stanford by a professor called Jack Baker. He does great work there. There are also work done by the Rose School in Italy. It also has collaborations with GEM that I talked about, the global earthquake model. So papers from GEM or universities like Stanford, or let me think of others, Illinois and
Berkeley.
Lehigh. Berkeley, I am not aware of people working especially in risk assessment, but they have a good earthquake department as well, but mostly seismology and ground motions. And those are the people who develop these NGA West ground motion prediction models, etc. So there is any California school actually is good for if you want to learn about earthquakes. But Stanford, universities from Italy, and Lehigh University in Pennsylvania, these are all good places where they talk about how we approach or what we are missing. Even Colorado University has a good program. So if you like look at the universities, find professors there, and just search their names, Google Scholar will just pop out articles, and it's much easier to look at articles than textbooks. So I think that's the better way to learn.
Thank you, Arjun. Thank you.
Yeah.
Thank you, sir. Does anyone have any more questions to be asked? I hope there are no more queries. I now call upon Catherine Joby to deliver the vote of thanks.
Thank you, Sanika. I deem it a great honor and privilege to propose a vote of thanks on this occasion. Before anything else, let me thank Almighty God for His grace and blessings in our lives. Our sincere thanks to the chief guest, Dr. Arjun Jayaprakash, Senior Earthquake Engineer, Karen and Clerk Company, Boston, Massachusetts, for gracing today's occasion. Indeed, it was a great opportunity to hear your thoughts on the challenges in earthquake catastrophe modeling, and this shall definitely encourage us in our future endeavors. Your thoughts have enlightened our minds and shown us a new path. A special mention to Dr. Unikarta Ji, our HOD, Civil Department FISAT, for being the catalyst that inspired us to do our best and who stood with us as a pillar of strength. With a deep sense of appreciation, I thank our loving teachers and students for their untiring efforts. I also thank each one of you for being attentive and sincerely cooperating with us. Thank you.
By that, we've come to the end of the session. Yes, sir.
Thank you. I just wanted to thank Arjun once again. That's all. Before
Okay. Yeah, I also want to thank everyone who are involved in this conference as such, and thank you, Reshma, for inviting me.
Yeah, it was a good lecture. It's very fantastic, excellent presentation and session. Thank you very much.
Thank you, sir.
So once again, I thank you, sir, for your valuable time. And thank you, everyone, for joining us today.
Better than if they just, am I right? Good point. Let's give it a try. Guess we do have to give voice.
Okay, so I think I'll step out now. So nice meeting everyone. Thank you.
yeah, thank you.
Thank you. Thank you. Not necessarily in that order. One, two, five. ഇട്ട് തരാം.
പോയി പോയി